Hi everybody, today we're going to go over the proof of this formula, which is the cosine of the sum of two angles. And before we get into this proof, let me just show you why proving this result is so vitally important to us. I'd like to bring up the formula sheet that we use. So this is the formula sheet that you guys have been using in class. And I want to scroll here to the back of it where we get these sum and difference formulas. And this is that formula that we are looking at. It's really only half of the formula because what I have written here is the sum of a plus or minus b, and this proof is only going to be the sum of a plus b. And the reason that it's so important for us to prove this result is because once we prove this result, we will be able to use that to get the other version of this formula. So if I can prove that the cosine of a plus b is equal to what I've said that it is, then it's easy to prove that the cosine of a minus b will be the formula where the sign in the middle has changed. I'll be able to use that first result in order to prove that. If I know that what the cosine of a plus or minus b is, I'll be able to use that result to find the sine of a plus or minus b. If I know what the sine and the cosine are, I'll be able to find the tangent. Turns out that the double angle formulas all come from these sum and difference formulas. The half angle formulas all come from the double angle formulas, which come from the sum and difference formulas. The power reducing formulas come from the double angle formulas, which come from the sum and difference formulas. So all of these formulas are going to end up coming from just this one result, and that's why it's so important that we make sure that we believe that it is true. Setting up this, just want to let you know of a couple of things that we will use throughout this, that the sum of the squares of the sine and the cosine are going to be equal to 1. So the sine squared plus the cosine squared of an angle is going to be equal to 1. We've seen that a lot. And then we will also use the even and odd formulas for sine and cosine. That is that the cosine of a negative angle is equal to the cosine of the positive of that angle, and that the sine of the negative angle is equal to negative the sine of the angle. So the cosine kind of swallows up negatives, and the sine takes negatives and spits them out in front of it. So we will use those throughout the course of this. All right, so we need to start with a picture, and I am going to give you just a moment here. So here is the picture, and I'm going to kind of draw this slowly so that you can keep up with it. I've started with a unit circle, and we're going to put a whole bunch of stuff on this unit circle. So as you're drawing the unit circle, probably want to give yourself some space on the page. I have labeled this one particular point x coordinate of 0, y, or x coordinate of 1, y coordinate of 0. And what I'm going to do to start is put an angle alpha in standard position. Now I've drawn this angle in the first quadrant, but there's nothing about this that requires that that angle is in the first quadrant. It could be in the second or third quadrant. It could be bigger than 2 pi. It doesn't matter. Just only matters that it is in standard position. And we know that if an angle is in standard position, then the x and y coordinate of where the terminal side intersects with the unit circle will be the cosine of the angle and the sine of the angle. So I know that this point right here is the cosine of alpha, sine of alpha. Now, the next thing that I'm going to do, and it's not really obvious why I am doing this. I'm doing it because it works, and we'll see why it works later on, is that I'm going to add to the angle alpha the angle beta. Now keep in mind, alpha was in standard position, beta is not in standard position. The initial side of beta is on the terminal side of alpha. So the angle that is in standard position is alpha plus beta. So going from the positive x-axis all the way around to where beta is, that angle in standard position is alpha plus beta. Again, beta does not have to be exactly this measure. Beta could be any size. This is just kind of I'm not specifying what the angle beta should be. Since alpha plus beta is in standard position, then I can find the x and y coordinate of that point, which will be the cosine of alpha plus beta and the sine of alpha plus beta. Again, you don't know why I'm doing this. You just have to make sure that what I'm doing is okay. Last angle that we're going to draw is the angle negative beta. So the measure of this angle and the measure of this angle will have the same absolute value. And we're just putting this in a negative direction. So from the positive x-axis, then moving in the clockwise direction, this distance or this angle has got to be the same as that angle. So this now is in standard position because it has the initial side on the positive x-axis. And therefore, I can tell you what the x and y coordinates of this one will be. It will be the cosine of negative beta and the sine of negative beta. As I said on that first slide, we're going to take advantage of the even and odd formulas. The cosine of negative beta is going to be the cosine of beta. The sine of negative beta is going to be negative the sine of beta. So I will rewrite that right there. Then what I'm going to take advantage of is that the way that I have set this thing up, and let me clear out some of that space there. The way that I have set this up is that the distance between this point right here, the cosine of alpha plus beta, sine of alpha plus beta, and the point 1, 0, has got to be the same as the distance between the cosine of alpha, sine of alpha, and the cosine of beta, negative sine of beta. That is, this line right here would have to be the same length as this line right here. And what you can see is that basically I've taken that angle of alpha plus beta and then I've rotated it around so that the distance between those points would always end up having to be the same. So the way that we are going to set this proof up, the way that we're going to write this proof out, is to use the distance formula on the distance between this point and this point has got to be the same as the distance between this point and this point. So make sure that you have these things written down. On my next slide, we're going to start writing out the distance formula in order to get, to simplify that and end up with the formula that we are trying to prove. Okay, so now we move on to the next part of deriving the formula. We have got this picture that we just spent some time designing. I know that the distance between this point and this point is going to have to be the same as the distance between this point and this point. And we are going to use the distance formula, and you see that I've written the distance formula in a slightly different format. Normally what you see in the distance formula is that this right side has got a big square root over it, and what I'm going to do is look at the square of the distance formula. So I'm calculating the distance squared, and that is a completely reasonable thing to do. It's going to make the math a lot easier if I don't have those square roots. All right, so what we're going to do is take the distance between the cosine of alpha plus beta, sine of alpha plus beta, and the point 1, 0, and then we're going to take the distance squared between the point cosine alpha, sine alpha, and cosine beta, negative sine alpha. All right, so what do we get? For the first pair, I'm going to get that the cosine of alpha plus beta minus 1 squared plus the sine of alpha plus beta minus 0 squared. So that will be the square of the distance between these first 2 points. And that has to be equal to the square of the distance between these 2 points. So that will be the cosine of alpha minus the cosine of beta squared. And then I'm going to add to that the difference in the y coordinates, which is going to be the sine of alpha minus a negative sine of beta. So that will be plus the sine of beta squared. So here is my starting point for the math that we are going to do. You can see that there's a whole bunch of things that are squared. So I'm going to be taking advantage of the fact that a plus b squared is equal to a squared plus 2ab plus b squared, as well as the fact that a minus b squared is a squared minus 2ab plus b squared, and we're going to be doing that a bunch. Right, so let's start. Let me square the first term. That will be the cosine of alpha plus beta squared minus 2 times the product of the two things, but one of them is a 1, so that's going to be 2 cosine of alpha plus beta, plus the last term squared, which is 1. So what I have written here in green is just this piece of the left side. Then I want to add to that what I get when I square this out. Well, that's a minus 0, so that doesn't need to be there. That will end up just being the sine squared of alpha plus beta. So there is the left side of the equation. Now I'm going to work on the right side. That will be the cosine of alpha minus cosine of beta. So that is the cosine squared of alpha minus 2 cosine of alpha cosine of beta plus the cosine squared of beta plus what I get when I square this term, which I'll put on a new line, sine squared of alpha plus 2 sine of alpha sine of beta plus the sine squared of beta. Okay, wow, that's a lot of stuff going on there. But hopefully you recognize that there's going to be a whole lot that simplifies. For example, this is the cosine squared of alpha plus beta. This is the sine squared of alpha plus beta. So those two are going to add together to be 1. On the right side, I have got the cosine squared of alpha, sine squared of alpha. That is going to be 1. And then I also have got the cosine squared of beta and the sine squared of beta. So those are going to combine to end up being 1. All right, so then let's see where we are. If I take this term and this term, those go together to be 1, and there's already a 1 there. So on the left side, I'm going to get 2 minus this piece, which is 2 cosine of alpha plus beta. That's what the left side looks like. On the right side, I've got this term and this term, which combine together to be 1, this term and this term, which combine together to be 1, so that's going to be 2. And then I've got these other two terms here. So that's minus 2 cosine of alpha cosine of beta plus 2 sine of alpha sine of beta. And if you keep an eye on where we are going, you can see that we are getting really, really close. If I subtract 2 from both sides, those are going to disappear. And then I've got a whole lot of 2's in there. So if I divide everything by negative 2, I will end up with the formula that I was looking for. That is that the cosine of alpha plus beta is equal to the cosine of alpha cosine of beta minus, I should have written that, this is a negative 2 right here, that minus the sine of alpha sine of beta, which was the result that we were trying to prove. Now, again, that seems like a lot because it is a lot, but I'm going to be able to use this result in order to prove the formula for cosine of alpha minus beta. I'm going to be able to use this result to do the sum and difference formulas for the sine and the tangent, and then that's going to lead to the double angle formulas and half angle formulas and lots of other things. We will not be starting from scratch on all of those.